So, we continue with our discussion on convective heat transfer, and yesterday I think I left you when we were talking about free convection versus forced convection, and I said that I want to take up another case where I am going to discuss the fully developed heat transfer, and that is going to follow once I finish the remaining part of discussion with free convection versus forced convection. Now, in most of the problems that we will encounter where we will have flow of a liquid metal, say for example in a furnace, in a ladle, or in any other kind of a reacting vessel, because the vessels are large and because we have refractories through which heat is being continuously lost. So, what is going to happen is that because of the stirring present in the system, and as we will see that all metallurgical vessels are essentially stirred because we want to expedite the reaction among various phases that we will discuss when we talk about mass transfer. So, given that there is an external stirring, so given that there is a forced convection and that the vessels are large, there is a finite amount of heat loss. So, we do not have a homogeneous system as far as temperature is concerned. We have temperature variations between different locations, and as a result of which free convection phenomena coexist with forced convection phenomena. Okay? So, but we have to now, I will introduce the number which we say that if you calculate the ratio of Grashoff's to Reynolds number square, this will give you the relative magnitude of free to forced heat transfer in such systems. So, for example, if we have this value much greater than 1, then we can say that it is a free convection dominated system. But in most of the metallurgical systems, as I said, particularly concerned with the liquid metals processing reactor, we will find it is other way around, and actually in our system we will have typically, except perhaps very close to the solid wall, etc., in a very big vessel where the stirrer is located far away from the walls, we can expect that there is going to be very weak convection currents near the wall or far away from the stirrer, and there maybe this condition is going to be violated. But for bulk of the reactors, because of our reactors are well agitated, so we will expect that these conditions to be fulfilled, and as a result of which free convection is not going to be of much importance to us. So, whether we are going to formulate a heat transfer, consider the free convection phenomena or not, we will, before we study if flow and heat transfer in a metallurgical vessel, we will compute this ratio, and then we will find out that whether free convection we have to take into account or not. Now, if you remember that if free convection is important, then we are going to consider one more forces. In the Navier-Stokes equation, whatever we have written earlier, and I have been writing for the flat plate geometry, I have included the inertial force, the gravitational force, the pressure force, and the viscous force. But when free convection phenomena are going to be important, and then the buoyancy force is to be also added to the fluid flow equation. So, we have one additional forces that come up into the picture. So, our equation, which is normally set of equations which are normally good for forced convective system, once we understand that this condition is not fulfilled, this is the condition that we have, or we will say that Grashoff's over Reynolds square is approximately is equal to 1, which essentially tells that free and forced convection are both important. In that case, what we are going to basically do is to take the Navier-Stokes equation, and in that graft a component which corresponds to the buoyancy force, and in that case I think this will represent the buoyancy force per unit volume. Okay? All the terms in the Navier-Stokes equation, as you all know, corresponds to force per unit volume term. So, if you calculate this or find out the resultant units or the dimensions of this particular term, you will find that because this is related with delta T, so that is why it is buoyancy force, and this is buoyancy force per unit volume, and this term is to be added to the momentum balance equation, okay, with an appropriate sign, because the buoyancy force is going to be acting vertically upward. So, then we will have on the left, in the Navier-Stokes equation, we will have the inertial force on the left hand side, then equal to, then we will have first the pressure force term, then the viscous force term, then the gravity force term, and then the buoyancy force term. Okay? So, that is going to be, so the expression, so the Navier-Stokes equation that we have derived for force convective situation as far as heat transfer is concerned, in that case we can make it adaptable to free convection phenomena also, particularly when this sort of a condition is fulfilled by adding this term. But what it essentially implies that in the Navier-Stokes equation now I have an unknown, rho is known to me, g is known to me, beta is known to me, coefficient of thermal expansion, but temperature is not known to me, delta T has to be evaluated. So, this tells us that the fluid flow and the heat transfer equations are going to be interrelated with each other. Okay? The heat transfer equation, as I have introduced in the context of the flat plate geometry, if you refer, then you see that there are already terms associated with fluid flow, and I said that look, to compute the heat transfer we will require the prescription of the flow, but here what happens is to compute the flow even we will require the information on T. So, we have a set of fluid flow equation, we have the thermal energy balance equation, the fluid flow equation in the context of the force, the flow over a flat plate was influencing the temperature field, but the temperature was not influencing the fluid flow. But in this particular case, when we have Grashopp's and Reynolds number square is approximately is equal to 1, that free convection is going to be equally important. In that case, what we are going to find? We are going to find that the temperature, the flow is going to influence the temperature, and the temperature in turn through the buoyancy force term will influence the momentum balance or the equation of motions or the motion per se in the system. So, we can say that the flat plate geometry equation that I had written yesterday, if you, I do not have to write it because these are already there on your lecture notes. Okay. So, if you remember, I wrote the equation of continuity here, equation of x direction motion and equation of y direction motion, and then the last equation was my thermal. It's a blank area, but you should be able to visualize when I am saying, you should be able to visualize that what I had written yesterday. Actually, I do not want to take much time and redoing the same thing. So, we had equation of continuity, overall continuity, equation of x direction motion, equation of y direction motion, and equation of thermal energy balance. So, the thermal energy balance in this case were related to the fluid flow because there were terms like rho u Ct, rho v Ct and so on in the thermal energy balance equation. On the other hand, this is a forced convection phenomenon, there was no free convection taken into account. So, the momentum balance equation did not contain this particular term. So, when you want to take Grashopp's and the Reynolds, when the Grashopp's and the Reynolds number square is close to 1 or not substantially different, in that case what I would say that we can consider that the flow and the heat transfer equations are going to be mutually coupled. Whatever I have written here is a coupling in the one way. That means, this essentially implies that the fluid flow, the heat transfer calculation depends on fluid flow, but the vice versa is not true. But in this case, what we are going to say, we are going to say that it is a two-way coupled phenomena, because the flow itself, fluid flow, will influence the heat transfer because of the term like rho u Ct etc. But in this case, the heat transfer will also influence the fluid flow because the free convection is driving the flow, and it is through this particular term, which is buoyancy force per unit volume term, which we have added to the axial direction, because G has no component along the lateral direction. So, this is the term which is valid only in the axial direction of the motion. Okay. So, this becomes a case of mutually coupling. So, when free convection is important, we have a mutually coupled heat transfer and fluid flow phenomena. When free convection is not important, we have a one-way coupling of fluid flow and heat transfer phenomena. Now, we have kinematic viscosity or momentum diffusivity, we have mass diffusivity, and we also have thermal diffusivity. If you look at the value, then typically this is the order. In the case of liquid metal, I would say, no, it is not valid for all fluid. Alpha, the thermal diffusivity is generally greater than, and is generally. So, this is the kind of relationship that thermal diffusivity momentum diffusivity and mass diffusivity. This is the smallest value of the order of 10 to the power minus 6, of the order of 10 to the power minus 6, of the order of 10 to the power minus 8 or 10 to the power minus 9, depend on what is diffusing actually. So, therefore, I have introduced a number called Prandtl number, and if you calculate the value, so this is nu by alpha, and you will find out alpha is greater. So, the Prandtl number for metal will come out to be less than or equal to 1. If you take for steel, for example, this value will come out to be about 0.2 or 0.3, something like that. Okay? So, this we must remember that metals have, small Prandtl numbers. The Prandtl numbers are very, very high. There are fluids which have much larger Prandtl number, and so on and so forth. Now, just to explain you that what we are going to, how we are going to do the calculations. So, I just want to illustrate that I had written 3 correlations on the last day, 2 convective heat transfer correlations and 2 forced convective heat transfer correlation, if you remember, one for flat plate and the other for spherical geometry, and the third correlation that I wrote was for a free convection from a vertical plate. Okay, I want to demonstrate in just one very brief discussion that how we can utilize these correlations in order to find out the fluxes and do certain macroscopic calculations. For every problem, as I have indicated, we are not going to do the elaborate solution of the fluid flow. So, spherical or sphere, and this I discussed with respect to your forced convection. And this is going, I said about free convection from a vertical plate. I wrote that Nusselts number L is equal to 0.5 into Reynolds number, Grashoff's number L 0.25, and this is Prandtl number. In some cases, these exponents, they depend on the geometry, they depend on the orientation, the type of flow, etc., as I have indicated yesterday. So, for some flow it is 0.33, for some flow it is 0.5, and we can have a product of Grashoff's number into Prandtl's number also in this case, which is, I think, Rayleigh's number. Okay? Now, the flux, as you have been, suppose if you take a case of a vertical plate of metal, say aluminum, which is dissolving in steel, and this is bulk steel. So, there is no motion, it is stagnant steel, liquid, and the steel is maintained. So, it is steel, and that steel is maintained at 1600 degrees centigrade. And if this is aluminum, obviously aluminum is going to melt in steel, because the melting point of aluminum is 760 degree. So, the surface temperature, although the geometry is going to shrink as a function of time as aluminum melts in steel, nonetheless the surface temperature in contact with the molten metal will always be the characteristic melting temperature of aluminum, and the heat flux in this case is the heat transfer coefficient times, I will say, 1600 degrees centigrade minus, I will not write centigrade, 770. That is basically, and the heat transfer coefficient will come from here, and the Nusselts number is equal to heat transfer, and this heat transfer coefficient, although we do not write, this is HL, this means plate average heat transfer coefficient, HL into characteristic length, which is the length of the plate divided by the thermal conductivity of the fluid. So, the moment I can find out, so I have to calculate Nusselts number. So, the starting point in this kind of a calculation should be that I want to first calculate the Nusselts number, okay, and for that I will have to calculate the Grashoff's number, and the Grashoff's number, as you know, yesterday I have given that expression That is what is the Grashoff's number. Okay? And this properties rho, mu, etc., they can be, because they are state properties, they can be evaluated at a mean temperature. For example, you have one temperature bound is here, upper bound, lower bound is here. You can take a mean temperature, which you call as a film temperature, and at that mean temperature, you can calculate for 1 atmosphere pressure and a mean temperature, what is the density of steel, what is the viscosity of steel, that you should be able to calculate. Okay? And then by substituting those density and viscosity values, you should be able to, given the plate length, you should be able to calculate the Grashoff's number. For Prandtl number, liquid steel's Prandtl number I have already said, we have calculated 0.16. Okay? So, if you substitute this, you get the value of Nusselts number, and in Nusselts number expression, if you get, substitute the value of L, where L represents the length, vertical length, and then use the thermal conductivity of the fluid, okay, which is something like 30 in SI unit, approximately I would say, and then you should be able to, because Nusselts number you have already calculated. So, you substitute the value of Nusselts number, and then you get the heat transfer coefficient from this, and then you go back here and then calculate the flux. And what you do with the flux, because you now know the rate at which heat is going to the solid, that rate is known per unit area. So, if you know the total surface area, you should be able to know that what is the wattage of energy that is going into the solid aluminum, and you know that what is the total heat requirement to melt this solid, which is the take the entire solid from its initial temperature to 770 degree centigrade, and then supply the latent heat. So, that is the total heat requirement, and if you divide it by the rate at which heat is coming in, which is Q multiplied by the surface area, then you get what is the complete melting time of this. And it is possible also that one can do an elaborate analysis by considering the fluid flow equations, by adding into the fluid flow equation the buoyancy force term, and then considering a heat transfer energy balance equation and fluid flow equations to be mutually coupled, okay, interrelated. One can have a framework, then one can calculate the heat fluxes, and one should be able to calculate the melting time by taking into account the moving boundary aspect of this particular problem itself. More elaborate solution or more detailed solution is possible by writing the governing equations of fluid flow and heat transfer in this particular case, and once you write those equations and solve those equations, you can take into account also the shrinking of the solid as a function of the time, and you can solve the equations in an unsteady mode, and then find out that at what time this solid has completely vanished into the system. But that is not necessary, that we have circumvented very easily, that we do not want to do that calculation. We have used this correlation, which is the result of some experiments or theoretical calculation, found out Nusselts number, found out heat transfer, found out the flux, then multiplying it with area, net rate of heat flow, and then once you know the total heat requirement for the melting process, we should be able to find out the time. That is a very simple but a very practical way of getting first hand and reasonably accurate, I would say, description of the complete melting time of the solid. So, we will solve some problems later on, and then that will give you a more bigger idea, more idea of how to use these correlations to our benefit. And as we will see that once you open textbooks and all, you will find there are plethora of correlations available to you, and you have to apply your judgment rationale to find out that which correlation you should be picking up for the system that you are investigating. And once that job is done, you should be able to find out that what are the heat fluxes, what is the net rate of heat transfer, and so on and so forth, and calculate many macroscopic parameters like complete melting time, etc. Now, I want to introduce the last bit of the fully developed heat transfer, convective heat transfer. So, we now talk about a forced convective scenario. Okay. So, we have studied this. So, we have a cylindrical pipe. It could be, I could have posed this problem, and these are so it's an infinitely long cylindrical pipe through which the flow is taking place. And there are a whole lot of problems which we have discussed earlier in the context of our discussion on fluid flow. I have said flow between parallel plates, fully developed film flow and so on. We want to now study fully developed heat transfer in the ambit of fully developed flow. So, we will assume that the flow is fully developed and we want to study fully developed heat transfer. I have defined what is fully developed flow, and I said that fully developed flows are those in which we have a constant pressure gradient or we have no acceleration of the flow in the streamwise direction. And this I have shown, or we know already, that the fully developed laminar flow. The treatment that I am going to elaborate now can be applied between, for example, two parallel infinitely long parallel plates, can be applied in a infinitely long film flow problem, and so on and so forth. So, wherever the flow is fully developed, we can apply the same law by assuming that what is fully developed heat transfer. Now, since heat transfer is taking place, so the fluid is coming here, for example, and what is the objective here? The significance of it is that the fluid may be cold fluid and the wall may be heated, and the heat may be going into the cold fluid may be taking heat, and progressively the temperature of the fluid may be increasing as a function of time. So, this wall maybe it can be maintained, as I said, either the heat flux could be constant, we can apply a constant heat flux here. So, if the heat flux is constant or the wall temperature is constant, we will see that the temperature of the fluid will keep on increasing as it travels, and at infinitely long distance there will be no heat transfer, because the temperature of the wall will be exactly equal to there is a state of thermal equilibrium between the fluid and the solid wall itself. But so long as the wall temperature is high, the fluid is entering the tube with a cold lower temperature, there is going to be heat transfer, and we want to find out that when can you say that the heat transfer is fully developed. Okay? It does not, we must understand that if the temperature does not change, then it has no meaning for us, because we want heat transfer to take place. So, the fully developed heat transfer is to be examined when there is a net flow of heat is taking place. Ultimately, in fluid flow, what happens? If I go from velocity here at this point, the velocity is same here, the velocity is same here, the velocity is same here. But if we say that fully developed heat transfer, temperature is same here, temperature is same here, temperature is same here, temperature is same here, that has no relevance, because there is no heat transfer then taking place. So, the definition of heat transfer, fully developed heat transfer, is substantially different from the definition of a fully developed flow itself. Flow profile is invariant along the streamwise direction, there is no acceleration along the streamwise direction. So, in this case, this is the z direction and this is radial direction. Okay. And let us say that we have constant wall heat flux and the length, that is what it is. I have drawn a section of it. Now, if you look at this flow, in that case we understand that there is, because it is along the z direction, it is infinite. So, which the z direction does not appear here. I have already said that infinite directions means the derivative is going to vanish, and we have a theta symmetry here. Okay. If you write down the energy balance equation, so it is a steady state problem, r theta z coordinate system problem, constant property, an idealization here, because the temperature is changing in reality, therefore, the values of density, viscosity, etc., will also keep on changing, because the fluid is entering here at low temperature, as it is traveling its temperature is changing, and as temperature changes we would expect thermophysical properties to also change. But we make this limiting assumption here, idealization here, that we want to deal it with constant property, and there is no free convection here, it is a purely forced convection scenario, and flow is fully developed. So, therefore, the moment I say flow is fully developed, we say that if Vz is the z component of the motion. So, we know this equation Vz is equal to Vz max in which R0 represents the radius of the tube. So, this condition is applied the moment I have assumed. Now, let us look at the thermal energy balance. So, therefore, I do not have to, in the case of flat plate geometry, when I had written yesterday, I wrote the fluid flow equations, I wrote the heat transfer equation, and I made one simplification yesterday when I was solving, that the velocity boundary layer was extremely small, such that I could, in the heat transfer equation, I could use the free stream velocity, for the velocity components that I had explained to you and I have shown to you also. And if you remember that, so I wrote this equation. This was my heat transfer equation. So, we have rho u Cpt, and then this was the equation rho v Cpt, and then I had this is the equation that I wrote. But I did this is the exact two-dimensional equation in Cartesian coordinate system, but I made this simplification the moment I assumed that one of the boundary layers, so it is much smaller, the velocity boundary layer. So, I said that this u, v becomes is equal to, now there is no v actually, v becomes is equal to 0, and this u becomes is equal to the free stream velocity u infinity, as a result of which I had taken it out, and then I have shown that this equation really, and this term is also was assumed to be 0, because we assume that there is a predominant direction of heat transfer because of the flow. So, it is a parabolic flow, parabolic heat transfer problem. So, as a result of which what happens, this looked like the equation which you have seen in the context of transient heat conduction in a semi-infinite geometry. That is what I have said. Okay? And because the moment I made that assumption, the three equations that I wrote for the fluid flow became redundant. I do not require any information on the flow, because the flow problem becomes much simple. Everywhere it is an uniform flow which is equal to u infinity, because one of the boundary layer thickness, or the velocity boundary layer thickness, was much smaller. In this case also a similar hypothesis will apply, because the velocity is already known to us. I do not have to consider the velocity. Okay? So, it is a one dimensional problem which I have solved for fully developed system, and this is the velocity profile that I have obtained. Okay? And because it is fully developed, so therefore, there is no second component. So, if you look at now the equations, for example, then you see that we have so Vz rho r Vr Cp into T, and then we have the K, and then we have partial z square, and then we have 1 by r. This becomes the third term I am not writing is the three-dimensional phenomena, because the theta asymmetry is there. So, the derivative with respect to theta becomes 0. Since the flow is assumed to be fully developed, so therefore, this Vz is exactly given by this expression, and this expression has nothing to do with the z derivative. So, this can be taken out, and also this term will vanish, because there is no radial component of the flow in the fully developed region itself. And this again following the same hypothesis that the flow is taking place in this particular direction. So, this term will also become is equal to 0. So, the equation now can be simplified. Okay? So, we can say that rho and then Vz. So, that I am going to write Vz over V max V max into 1 minus r square by r square or r 0 square, because that is the radius, okay, and then Cp is also taken out, and then this is. And this is going to be equal to 1 by r, so it's k, and then you can write it like this, k by r. That becomes the equation. Now we will introduce the definition of fully developed heat transfer, and we will show one more thing. The fully developed heat transfer implies that the streamwise variation of is equal to the rate of change of temperature along the direction of the flow is exactly equal to the rate, and this is equal to constant. I have introduced a term here dTB, which we call as a bulk temperature. What is that bulk temperature? The bulk temperature essentially is a cross sectional average temperature. So, TB by definition is equal to integral T 2 pi r dr 0 to r 0 divided by pi r 0 square, cross sectional average temperature. So, suppose if you take, that is what it implies. So, I can erase this to make you understand. Okay. So, if you take here, you imagine this is a circular cross sectional area inside the tube. So, the temperature in this shaded area is actually the TB. So, this TB, where actual temperature is going to be, the moment I average it over this area, the radial dependence of the temperature is eliminated. So, TB is therefore only a function of Z. It is, so, I will have one TB here, another TB here, another TB here, and so on and so forth. So, at this cross section, at this length, one single TB is going to be obtained, because I have integrated the temperature with respect to time, with respect to radial distance, and therefore, that dependences. Normally, as far as this equation is concerned, T is a function of both R and Z. That is what it is. But the moment I do a time averaging along the radial direction, then I find out, or I can say actually, if I represent it like this, you can interpret that SAR has implied that this T bar is actually an integral of this T around from R is equal to 0 to R 0. That is what it is. And instead of writing is T bar, we call it as TB, the bulk temperature. So, when this condition is fulfilled, that the rate of increase of temperature along the Z direction is exactly is equal to dTB, the consequence of this is that the Nusselts number will come out to be constant. This is the consequence of this. So, a fully developed heat transfer is characterized by a constant Nusselts number evaluated at the wall. If you evaluate the wall heat flux, okay, and then you will find out that the Nusselts number comes out to be constant. Now, what is the definition of Nusselts number? The Nusselts number definition, you all know that in this case, Nusselts number is equal to, we have heat transfer coefficient into characteristic length, diameter, or you can say Nusselts diameter, and this is equal to K fluid. And what is this heat transfer coefficient? The heat transfer coefficient in this case is defined by the wall heat flux W minus or TB minus TW. Wall temperature is higher, fluid temperature is so like this. H times delta T is equal to. So, that is the definition of H, and that is the definition of the Nusselts number that applies, and this Nusselts number, as I have indicated, this will come out to be constant. Now, you can, for example, the moment you substitute what is dTB, now let us see that how can you convert this equation. I will just do few steps and then leave the final solution for you to carry it out in your hostel. Okay? And I want to show you that with this assumption that when the flow is fully developed and the heat transfer becomes fully developed, or the Nusselts number is constant, in that case this partial differential equation will translate into an ordinary differential equation. Let us see what happens. If you take two such segments, so you have one is here is we have TB1 and another here is TB2, 1 and 2. A very small cylindrical segment. Now, the bulk temperature changes here, and you can see that whatever is the change, and there is a mass flow rate here, right. It is also possible to replace this term by 2 times Vz average. You all know that we have discussed also, that the Vz max is equal to 2 times of the Vz average that came out from the fully developed flow analysis. So, that approximation will also hold good. We have a mass flow rate here. That mass flow rate is equal to rho times V times area, and that is rho times Vz average and to area, and that is equal to pi r0 square. That also when you did macroscopic mass momentum balance, we have found out. So, this is m dot mass flow rate in kg per second. Now, when heat is coming out under steady state condition, so we can say m dot Cp, okay, and because the temperature is increasing as a function of time, so I can write it like this: m dot Cp into Tb2 minus m dot Cp Tb1, which essentially represents the net change. If this is the 2 cylindrical, or a small cylindrical segment, which is bounded by 2 surfaces, and I want to do, I am performing an energy balance. So, heat coming in and heat going out, and that must be related to the heat flux which is coming into the system. So, heat going out minus heat coming in, okay, must be equal to, under steady state condition, is equal to QW is the wall heat flux multiplied by 2 pi R0 into Z. Or I can say delta Z. If delta Z represents the distance between this and this. And therefore, I can say that m dot Cp delta Tb is equal to QW into 2 pi R0 into delta Z, or delta Tb by delta Z, that is equal to QW 2 pi R0 divided by m dot into Cp, under the condition that delta Z is very small. So, you can say that dTb dz, or variation of temperature along the z direction, is given in terms of the wall heat flux multiplied by 2 pi R0 into m dot Cp, and that m dot is equal to, as I have written here, rho Vz average into pi R0 square. So, I can change this, so I can have this, and then I can write it here just 2 remains 2 pi R0, pi and R0 square. So, that is the final expression. And as you can see here, this is constant, this is constant, this is constant, and heat flux is a constant heat flux that we have already assumed. So, therefore, it is understood that this term is equal to constant. So, if we now replace this term by dt b dz as per our definition, then what we find out that this derivative can be replaced by this particular term itself. And what does this indicate? Then the left hand side will be only a function of r and nothing else. And then therefore, what we see here that this equation which we had written will get converted into from a partial because this derivative will vanish now. This derivative will be replaced by dt b dz and will be replaced by a constant term, and this left hand side being a function of r. So, therefore, the r z dependence is going to be vanished and we will have only r dependence. So, therefore, this partial differential equation now will be translated into an ordinary differential equation, and that ordinary differential equation will look like, I will write the right hand side first, and that right hand side will look like 1 by r and we had here what? Rho Vz average into 2 1 minus r square by r0 square, and now dt b dz that I have found out is equal to qw. So, it is equal to 2 qw, and this is going to be what is the parameter? Okay. Rho, there is a Cp term is also here. Okay. So, I think Cp is here, so I missed it. 2 times Cp, okay, rho V average, and then here we have rho Vz average and here we have m dot Cp. So, m dot is equal to this. So, here we have a Cp term also. So, we have rho Vz average R0 into Cp. So, this cancels out, this cancels out, Vz average cancels out, Vz average cancels out, Cp cancels out, Cp cancels out. Okay? And then what we are going to have here is the final expression looks like four times qw into 1 by r square. What are the boundary conditions? The boundary conditions are r is equal to 0, we have minus k dt dr, the flux is because of the symmetry property, and r is equal to Rw or R0, we have T is equal to Tw. Note that this Tw is an unknown parameter. The boundary condition is given only in terms of Qw. So, this Tw actually is a function of the wall position. Because I want to introduce this Tw here, because I want, if you remember, I have written the Nusselts number in the heat flux expression where I have written that the heat flux, heat transfer coefficient is equal to Qw divided by delta T, and that delta T is equivalent to Tb minus Tw. So, that is why I have cast the boundary condition into this particular form. So, now one can solve this equation, and the solution now I am not going to discuss because it is a straightforward simple solution, because the boundary conditions are going to be given. One of the constants will vanish because r will appear in the denominator when you integrate, and then you should be able to find out from this that as a function of r. That relationship you will be able to establish. And of course, in that expression you will have Tw coming in because it is coming from the boundary condition itself. Now, once you have gotten this, what you can do? You can find out everything. So, you can find out Tb also, and Tb, as I said, pi r0 square integral 0 to r0 t 2 pi r dr. So, you substitute this functional expression, you are going to get Tb. Once you have obtained Tb, then you can go back to the expression whatever I have written, that H is equal to QW TB minus, sorry, this is I wrote T1 minus TB. So, having obtained that T, you can substitute it here, and then you will say that you have the Nusselts number, which is equal to 2 times H. So, 2 times QW, and then this is characteristic length, which is D, and then this D is equal to, if you do it R0, then you will get 4, okay? And then you can get no, I have written QW, so let me not do it hurriedly. So, let me do that. So, the final equation I have written here, so it is there, so that is fine. And then the heat transfer definition is there, and Nusselts number is equal to H d0 d by kf, and H is equal to this. So, you can write QW, okay, divided by TW minus TB and then you can set R0 by K sub f. And you can see here, when you will integrate this, you will have a very similar expression like this when you integrate this particular term and determine the TB. And once you substitute the TB here, the TW will cancel out, QW will cancel out, and then the Nusselts number will result to a constant value here, and this constant value I think is 1.56. That is what will come. So, this I leave for you, because I want to finish the discussion. I have to start next lecture, radiation. So, now we have the governing equation is there, you apply the boundary conditions, you find out the temperature profile. Having determined the temperature profile, you find out that what is the expression for the bulk temperature. Use that bulk temperature expression here, and then you manipulate this equation in order to find out that what is the Nusselts number, and you will see the Nusselts number comes out to be 1.56. And I leave it up to you to try it in your hostel room. This is only 80% of the job I have done. This 20% I would expect you to do, and then you can see that the condition that we have applied, that when these conditions are fulfilled, that the rate of change of temperature along the z direction is equal to the rate of change of bulk temperature, and this assumes a unique value, okay? And the consequence of this is that constant Nusselts number must result, and this is the proof that yes, the Nusselts number has indeed come out to be 1.56. So, we should be satisfied at the end of the day. Okay, so we will finish here. So, tomorrow we will start with the discussion on radiative heat transfer, and then I think we should be ready to discuss various applications of the heat transfer theory to metals processing. And I would like to take at least, as per I think the course handout that I had given you, I think 3 lectures have to be devoted as far as the application part is concerned, but radiation I think I will need about 1.5 to 2 lectures in order to give you the gist, and following that 2 or 3 lectures I will talk about 2-3 interesting problems which are which will give you an idea that how the heat transfer fundamentals are applied to metals processing, and what sort of an information one can obtain from the application of the theory to the processes.